Hey guys, I hope you guys are having a great Monday. This is going to be a really short, sweet, um, comprehensive going over the whole study guide that was passed out. For my afternoon classes, please remember that your test is on Wednesday. For my morning classes for second and third, please remember that your test is tomorrow. Um, Feel free to message me if you have any questions or if you have any concerns. Again, for my afternoon classes, all of this is in the PowerPoints, all of this is in the handouts, the works, the notes, um, the guided notes from the videos that we've watched. So if you are struggling with a particular topic, please go to the e-class. Please look at the content. Please look at Unit 3 solutions. And also, do not forget that if you need even more help or instructional help, that there are already made videos for you in the second semester chemistry help support videos. And they have PowerPoints, and this covers everything that we are supposed to be doing. So here is a copy of the study guide. Feel free to pause this video, make sure that to write down the correct information, especially since I'm going to try to go through this very, very quickly, not too quickly, but enough to where this is not a super long video, because I know some of you do not like the ramble. All right. So in number one, in a solution, the solute is the substance that gets dissolved. Again, examples of solutes that we've talked about in class: sugar, salt, different ones like that. In a solution, the solvent is the substance that does the dissolving. Remember that the most universal number one solvent in the world is water. So the water, H2O, as the solvent, takes and pulls and does the dissolving of, let's say, sodium chloride, salt. Again, that process is solvation. All right. Number 4, water is polar. So because it's polar, it can dissolve ionic substances because like dissolves like. Remember that oils do not interact with water. They are immiscible to each other because water is polar and oil is nonpolar. All right, next. True or false? Answer is false. A solvent of a solution does not always have to be a liquid. So try to remember us talking about gases and different types of mixtures, solids, when they are able to dissolve with each other. All right, number 6. So this question is referring to number 5. So if it's a false, give an example of supporting your answer for number 5. Well, air, nitrogen, is the solvent. It does the dissolving. 7. Now, hint, hint, wink, wink. If you have pure air, something pure, pure gold, pure silver, pure air, that is a pure substance. That is not a mixture. That is just a substance. So it's not heterogeneous, it's not homogeneous, it's just a substance. All right. Number 7, when a solute can dissolve in a solvent, this is called being soluble, from solubility, the ability to dissolve. When the solute and solvent are both liquid, so you have two liquids that can dissolve into each other. In my classes, we use the example when you take those Powerade drops, liquid drops that you add to water to make a drink. They have them at the grocery store. They're like super concentrated, and you just like add like a few drops into your water so you can have Powerade, lemonade, anything like that. It's a liquid going into a liquid. This is called being miscible. Now, number 8, when you have a solute who cannot dissolve, this is being insoluble. They do not dissolve into each other. And we'll get into some examples here in a second. When the solute and the solvent are both liquids, such as oil and water, like we talk about in number 10, that is it being immiscible. They do not dissolve together. Yes, you can shake them up. Yes, they can make an amazing salad dressing, but they do not dissolve into each other. They stay separated. All right. Sorry, guys. 9. So this is referring back to question 7. Question 7 talking about soluble and being immiscible with 2 liquids. So 2 examples of a solution described in 7. Salt and water, sugar and water, tea. All of these, when you're talking about something that can be soluble, is going to be an example of those. Now, number 10 refers to question 8. So oil and water, sand and water, they don't mix. They are immiscible to each other. Sand and water, you can have filtration and separate out. So, number 11, explain what happens to a solute during the process of solvation. So the solute is surrounded. The solvent surrounds the solute. So this water surrounds those sodium chloride molecules, and they break them apart and pull them apart. That is the process of solvation. All right, 12. When the scattering of light by a heterogeneous mixture, a heterogeneous solution, this is referred to the Tyndall effect. Now, there is one type of homogeneous that can scatter light. That's called colloids. Colloids. All right. Questions 14, 15, 16, 17, and 18 all refer to this beautiful solubility curve. If you do not know how to read this, I lovingly, strongly suggest that you definitely watch some videos on it and discuss, message me about this. So, Y axis. X axis has the temperatures, Y has the grams of the solvent per 100 grams of, not the solvent, the solute, sorry. The grams of the solute per the 100 grams of the H2O solvent. So, all they're asking you in number 14 is, what's the solubility? What are the grams of potassium nitrate at 40 degrees Celsius, 50 degrees Celsius, and 70 degrees Celsius? So, 62 grams is going to be at 40 degrees Celsius because, 1, we are trying to find KNO3, which his line is right here. When you start at the 50 and you intersect with that solubility line, it puts you, 40, it puts you right above the line of 60, thus being 62 grams. At 50 degrees Celsius, it is intersected right on the 80%, 80 grams. Then at 70 degrees Celsius, all the way up here, it intersects right on the 130 grams. So what temperature do KNO3 and KCl have the same solubility? So you have to first identify each of the lines. So KNO3 is here, and KCl, potassium chloride, is here, meaning that they intersect, crisscross, come together right here at 20 degrees Celsius. Remember that it didn't ask for the grams, it asked for the temperature. So make sure that you have that correct on your sheet, because I know some of you swap that in your head. All right. Number 16, which compounds are gases? That is NH3, ammonia, and ammonium, and Ce2, parentheses SO4, close parentheses 3. Now, we are able to tell, even though there's not a little key, that both of these are gases, because if you notice, as I'm waving this arrow thing, they go downward. Each of the lines scoop downward, where for solids, they're going to be going upward. So please notice the difference in the direction of your line. All right. Now, how much KClO3 will dissolve in 300 grams of H2O saturated solution at 50 degrees Celsius? So please remember that this chart is talking about 100 grams of the solvent, H2O. But now, I don't have 100 grams, I have 300 grams of my solvent. So that means whatever the grams lie on this chart at 50 degrees Celsius for KClO3, we are going to have to increase that by 3 times, because taking 300 divided by 100 gives you 3. Think about it this way. If I have 3 batches of cookies and I need to use 2 eggs in each batch, that means I'm going to use a total of 6 eggs to be able to make 3 batches of cookies. So when I have just a regular plot on the KClO3, which is right here, I end up for 50 degrees Celsius at 20 grams. So 3 times 20 grams gives me 60 grams total. Please make sure you show your work. All right, now for number 18, this is literally just asking you, hey, is it saturated, unsaturated, supersaturated? 60 grams of NH4Cl at 70 degrees Celsius is going to be saturated. B, for 80 grams of KNO3 at 70 degrees Celsius is unsaturated. 15 grams of KClO3 at 40 degrees Celsius is saturated. D, 35 grams of NaCl at 50 degrees Celsius is going to be unsaturated. Please remember, and we're going to look at the NaCl, sodium chloride line, which is right here, straight across. His line anything above this line plotted on this graph is going to be super saturated. Anything on the line, physically on the line of NaCl, is saturated. Then anything below this line, if you're just thinking about just this line in the plots, is going to be unsaturated. All right, next page. Number 19. What are 3 ways to increase the rate of solvation? Remember that solvation is literally the solvent surrounding the solute and pulling them apart. So things being dissolved. Now, how can I speed up this process? If I am in a hurry in the morning and I want my sugar to dissolve quicker in my coffee, I may want to make sure, 1, that it's warm, that it is a warm coffee. 2, if I put those chunks of sugar into it, I can literally break it up. Or possibly 3, as I'm running out the door, I could be swirling it and shaking it and try to have that sugar dissolve very quickly. All right, number 20. As you increase the temperature of a solid, the solubility increases. So, raise the temperature, you raise the solubility. That is proven with solids here, that if I am raising the temperature, so you see how the x-axis increases from 0 to 100 degrees Celsius. As I raise the temperature with solids, they increase in their solubility, being able to dissolve more of the substance. All right. 21. As you increase the temperature of a gas, the solubility does the reverse. Remember that we talked about soda a lot and us having to be able to decrease the temperature, decreasing the pressure to be able to increase the solubility for that syrupy soda liquid to take in CO2, to be able to cause it to become, as you know, soda. So, you can also tell by the lines here that the lines going down are your solvents as gases. Now, NH3 starts up pretty high at being able to dissolve 90 grams of the solute and decreasing its ability to dissolve into water due to the temperature increasing. All right. So 22, what happens to the following types of solutions if you add more solute? Great question. So saturated, if it is saturated, the solute dissolves. If it is unsaturated, your solute dissolves. Now, if you are super saturated, that means your solute's going to drop out of the solution. Remember that we did rock candy, we did the borax, where we made crystals. This is what happens with super saturated solutions, that literally the solute, so example, the rock candy, the sugar, had no one to bond with. He didn't have any extra water molecules to bond and come together with. So thus, over time, which we're going to see tomorrow in the next couple days, crystals start to form, crystallization, causing them to drop out of the solution and become back to a solid. 23. Are the following substances heterogeneous or homogeneous? Remember, hetero, separate, homo, together. So, air. When you have a mixture of air, this is not pure air, it is homogeneous. When you have salt water, it is homogeneous. When you have soil, think of everything in your soil. It is heterogeneous, like trail mix. D, oil and water. That's going to be hetero because they're still separated. An alloy is going to be hetero. We use the example for an alloy as brass. You can't find brass on the periodic table, but you can make brass by mixing two solids by copper and zinc. Then HOMO for Kool-Aid. All right, 24. In the following table, fill in the information. So filtration, which we are able to talk about, is the separation on particles in filters. Large particles get stuck. Example, coffee. Love it. Love the coffee. So Misty makes her coffee in the morning. She has her filter paper, and it catches all of the coffee grinds so they're not in her coffee, her solution. So another example of this is sand and H2O. Distillation. So this is the separation based on boiling point. Another one, any HOMO solutions, the supersaturated we are able to start making, but if we didn't make it supersaturated, but we just added the sugar and to the warm water and had a saturated solution or even an unsaturated solution, so separation based on the boiling point. If we let that sugar or salt water boil out and just continue to boil where the water leaves and the other substances stays behind, what's going to happen is we're going to get rings of crystals on the side because there's no more water there. All right, crystallization. This is when you have a supersaturated solution dominantly. The formation of a solid. So with the rock candy, over time, it will form into crystals because they're going to bond with each other again and form a solid. We also did this by making the crystals from the borax in second and third period. All right, chromatography. So this is about ink, being able to separate based on size up a column. Remember that we talked about the different letters, different ink companies have different recipes for theirs, and you can figure out who wrote the letter or where the ink came from or what time period based on that. All right, what are colligative properties? Properties that depend on how many solute particles are present, or concentration, not what the particle is. That is just a straight definition. I know for a fact that this is listed in the PowerPoints. All right, so some examples of colligative properties that we were able to discuss. So vapor pressure lowering. This is less solvent becomes gas. Boiling point, elevation, higher boiling points, so the need to increase the temperature to boil. Freezing point depression is the lowering temperature to freeze. So back to boiling real fast, boiling point. Remember that when we add a solute into a solvent, that no longer means that it's going to have a consistent, it doesn't have the original boiling point. Example, having antifreeze in water. You will find this in your car, antifreeze. Now, granted, it helps your car's engine, the transmission, not to freeze in the winter, but it also increases the boiling point where it doesn't overheat and have it boil over until it's an extremely high temperature. And it must be an extremely low temperature in order for it to freeze. All right, osmotic pressure increases. H2O moves in, so the pressure increases. You've talked about this in class, and you are able to talk about this in biology. It is exactly what you're thinking with osmosis, osmotic pressure that you learned about in biology. All right, molarity and dilution calculations. Now, this is where a lot of people have struggled. So please, please, please message me if you have any questions or concerns. So 27, this is going to be an M1V1 equals M2V2 equation. They tell you that you are trying to find how many milliliters of a 5.0 molarity of H2SO4 solution. Now, remember what I said about the word of, that they connect what came before and after that word. So, meaning that 100 milliliters of 0.25 molarity of H2SO4 will be together. So for M1, we put 5 molarity times X because we don't know what V1 is. But we do know that our M2 is a 0.25 molarity times 100 milliliters. When you are able to multiply that, so that's 25, divide by 5, it gives you 5 milliliters. 28. What is the molarity of 5.5 liters of solution made from a 38 grams of potassium nitrate? All right, so first off, 1. This is your pyramid. So you guys are on a pillow. This is your pyramid. This is where up top of your pyramid, moles, bottom, molarity, to the side, liters. You have to have them in moles, molarity, or liters in order to be able to solve anything in your pyramid. So the first thing you need to do with 28 is take that 38 grams of KNO3 and make him into a mole. Convert him. So you have 38 grams. Divide by 101.11 because that is the molar mass of KNO3. And that gives you 0.376 moles. Now, when you're trying to find molarity, moles go on top, liters go on bottom. Your final answer should be 0.068 molarity. Big M, big fat M. Please do not forget that. All right, 29. How many grams of NaSO4 are needed to prepare 250 milliliters of a 1.6 molarity solution? So again, we need to be able to convert our milliliters to liters. Well, you have to convert and make sure that all the units for your triangle when you're trying to solve are either molarity, moles, liters, not grams, not milliliters. But with your M1 V1 equals M2 V2, you can do it with milliliters. So keep that in mind. All right. So 29, convert 250 milliliters, divide by 1,000, or move the decimal over 3 spots, giving you a 0.25 liters. Then you want to be able to take the 1.6 molarity, and this is a different setup than you guys have normally seen it, which is okay. Moles over liters. You're trying to find moles, you have molarity, so thus you're going to need to have moles times liters, giving you a 0.4 moles. Remember that moles, you're able to literally multiply molarity times liters. So, but they're not asking you to end with a mole. They're asking you to end with a gram. So you need to be able to, in this case, multiply your moles of given, so what you just found, times the molar mass of Na2SO4. thus giving you a final answer of 56.8 grams. All right, number 30. What is the molarity of a substance made by adding 130 grams of Li2SO4 to 0.9 liters? So this is going to be a pyramid again, a triangle. And you're able to take the grams that you are given, the 130 of lithium Li2SO4, and you're going from grams to inside the triangle. So that means you just need to divide by the molar mass. So 130 divided by the molar mass of Li2SO4 gives you a 1.18 moles. Then for molarity, you are able to solve by having moles on top, liters on bottom. You don't need to do anything to liters. He's already in liters, so just put them in, giving you a 1.31 molarity. So 31, how many grams of AgNO3 are needed to make 320 milliliters of a 2.2 molarity solution? Now, this is a triangle again. It's really easy to figure out who's your triangles if you only are given two numbers, and moles, liters, or molarity, and they ask you for a third one, it's going to be a triangle. If they give you three numbers and they're asking you to find a fourth one, that's going to be M1V1 equals M2V2. All right. How many grams of AgNO3 are needed to make 320 milliliters of a 2.2 molarity solution? Now, please keep in mind that this is not in liters. So one, we have to be able to take our milliliters, 320, to liters. So thus we can either, 1, find the decimal over 3 spots, or 2, divide it by 1,000. Whatever makes sense to you. So 320 divided by 1,000 gives you 0.32 liters. Then you're able to solve for the unknown moles by having molarity, the 2.2 molarity that was given, times the 0.32 liters that you converted. That gives you 0.704 moles. Now, that 0.704 moles is not what you end up with. So thus, you need to be able to take it from moles to grams. So you're going from inside the pyramid to outside. So you're going to multiply. So you multiply the 0.704 times the molar mass of AgNO3, giving you a 119.6 grams. Number 32. This is a M1V1 equals M2V2 type of problem. They tell you what volume of a 6.0 molarity Ki solution would be used to make a 0.3 liters of a 1.25 molarity Ki solution. Now, notice, here we go. The first of is not connected to a second number. So meaning that guy right there, that 6.0 molarity is going to be connected to the unknown volume. Then a 0.3 liters of a 1.25 molarity of potassium iodide are able to go for your M2V2. They are connected. There are two numbers together. They are married. They're all in it together. So they go on one side of your equal sign, where your first molarity, 6.0 molarity, goes with your unknown volume on the other side. So when you have a 6.0 molarity times X equaling 0.3 liters times 1.25 molarity, it gives you a volume for V1 being 0.0625 liters. All right. If you dilute 80 milliliters of a 9.5 molarity solution to make, so we're going from having 80 milliliters of the solution and now increasing it to 700 milliliters of the solution. So what's the molarity of the diluted solution? Going from super concentrated, now we're at 700 milliliters. So what is our molarity? Because we didn't add in more stuff. So what is the volume? Is going to be your V1. Sorry, it's reading from the top. I was reading from 32. So 80 milliliters is going to be your V1. 9.5 molarity is going to be your M1. Your 700 milliliters is your V2. You do not know your M2 right now. So when you take 80 times 9.5 equaling the unknown, V2, times 70, you are able to get V2 as a 1.1 molarity. Please notice that it has gone from having a high concentration, a high molarity, downward. All right. I really hope you guys are able to answer these questions, and please message me if you have any questions or concerns. This is going to be the end of the study guide for my afternoon classes for 5th, 6th, 7th. Please, please, please look at the information on eClass. I hope you guys have a great night, and I will see you tomorrow. Bye.